This is the webinar, New Opportunities for Weather and Health Research. This is an opportunity to really just sort of exchange some knowledge between a couple of groups. In the first part of the call, we're really lucky to have a number of people telling us about the different health databases they work with. And then folks from Environment Canada have been kind enough to take some time to tell us about the kinds of data they're preparing, some of the stuff they're working on now that'll become soon available. And so Didier, I'll get you to star your phone, and maybe you can give us a bit of an intro to who you are, and we'll move on from there.
Yes, hello. My name is Didier Devignon, so I work at the Meteorological Service of Canada. I'm Chief of the Air Quality Modeling Application section in the Canadian Meteorological Center operations here. Next slide. I was asked, I think, to my discussion with Eleanor, I understood that it would be useful that I provide a little intro to how we produce modeling data, or what we mean by the modeling data or the analysis data that we can offer to the community. So next slide. I'll start with the air quality, as this is the data that we first shared with or started discussions with the CANUE consortium. So in air quality, in order to represent the air quality, we need to model various processes in the atmosphere. And one of these, at the bottom left, are the emissions. It is very important to capture the emissions of pollutants to the atmosphere correctly to get a representation of air quality in the atmosphere. And we are trying to resolve all these processes in a numerical model. So next slide. What the numerical model is actually we're trying to represent the atmosphere, and this representation is done by decomposing the atmosphere in boxes, so a 3D grid, and all these small boxes have parameters that represent their physical properties of the air, humidity, temperature, etc., but also in our case various concentrations of pollutants, not only the pollutants of interest, but various chemicals that play a role in the chemical interaction. Our current operational system is illustrated here. It's covering all of North America in blue. I know the image is not very clear, but so it's from Texas essentially to Greenland, and the surface resolution is 10 kilometers. So next slide. I'm just trying to illustrate the process that we use to resolve the evolution of the pollutants in the atmosphere. So we start with a description of the initial state of the atmosphere with concentrations of pollutants. For that, we have to use whatever observations are available, and then we add pollutant emissions in yellow at the top. Also, we resolve the evolution of the weather, and that allows us to calculate the transportation of these pollutants by the winds, and then we consider the amount of radiations or the temperature to calculate chemical reactions within all these parcels of atmosphere, and removal by rain, etc., deposition to the ground. So this provides a forecast of air quality, but we do it by decomposing time as well through little time steps. But, in this example, I'm using a time step of 15 minutes. So we resolve these using mathematical equations that represent all these processes, and we do it again for the next time step, etc., until we get to the whole time frame of our forecast. In our case, it's 48 hours so far. For weather, it's very similar, but they go much further in the future. And they put more care on the resolution of the weather itself, and they don't have to take into account the chemical reaction. So in order to provide, next slide, in order to provide this initial state, in numerical models, and I'm talking here more in general for weather forecasts as well as for air quality, well, we need to use as much information as we can from the observations. For air quality, we don't have so many observations, but for weather, we have lots of remote sensing observations from satellites and measurements from balloon, etc. And in order to create initial conditions, we use very sophisticated techniques called data assimilation. And these techniques, I won't explain the details, but what they do is they provide the state of the modeled atmosphere that is as close as possible to the observation, but still keeping a physical coherence in the model. So it's really a mathematical minimization problem. What we can do, and this is very CPU intensive, so we're doing it for the weather, and so far we're not doing it for air quality yet, but we can produce what we call objective analysis, which uses a similar approach, but without the minimization. So we're combining a model, a short-term model forecast with observations. So let's say a 6-hour forecast that was done 6 hours ago with observations of surface air quality right now, and through that we produce an estimate of the current status of the air quality at the surface everywhere. So next slide shows illustrates how this can look like. So at the upper left, you can see a map of North America. In this case, we're showing ozone, a model, short-term model forecast of ozone. And in the bottom left, you see a map of the available surface observation of ozone. All these little dots represent a station in the model. And the algorithm combines these and produces at the right what we call the objective analysis for air quality. And in this example, you can see that what we call the trial, the upper left estimate by the model, is corrected by the observations because on the right you can see that the algorithm corrected, reduced the amount of ozone in southern Quebec in this example, and increased it in Alberta. So we believe that this provides the best possible estimate or compromise estimate of air quality for that given time. And it has the advantage to cover all the domain as opposed to the observations that are really valid only where they are measured. So we do that not only for ozone, but also for NO2, NO, PM2.5, PM10, and SO2. Next slide, we're showing the data sets that we have for air quality analysis, surface analysis. So we started to produce them in the experimental mode in the early 2000s, so 2002, we started with ozone. Then PM2.5 was added a little bit later, and we started to run in operations and to produce more continuous data sets really in 2013, actually. So since 2013, we have an operational data set that's really complete and valid. And in 2015, we added a few other species such as PM10 and NO and SO2. So on next slide, I just wanted to address also other questions that were raised in the preparation of this meeting. It seems that the health community is sometimes confused about the available climate data. So we'd like to stress that the MSC and Soil Environment Canada is, we believe, the main reference in Canada for climate archives. And our archives, of course, are measured at the stations, and they're offered as and they can be accessed. But these data sets really are station measurements, and so therefore follow very strict guidelines, and they can be considered as being coherent and consistent through time. So there are a few instructions here as to how to access these these data sets. And of course, some provinces may have a little bit more data or more stations that they're taking charge of, and that they're not always sharing all this data with the national archives, but really the MSC has the most coherent, I think, data set. So next slide. I just wanted to present that we are aware that there are other sources in Canada. So NRCan, for example, is advertising climate data, but it really was based on ECCC archives. But we did a reprocessing of it using interpolation algorithms to provide a regular grid of data. Similarly, you also the consortium PKIC and Uranus that provide climate services and can provide some climate data. There are groups that are in charge of trying to produce regional climate modeling, but they really have a more regional focus. Typically, the data sets provided by PKIC are valid in BC, and Uranus mostly valid in Quebec. They do use also interpolation algorithms, but they're a bit more sophisticated, take into account the topology, for example, to correct and produce something that is presented at a higher resolution. Now, on next slide, I want to present another approach to looking at past weather data, and we call it the Reanalysis or reforecast product. So Environment Canada is interested in producing these forecasts. So what is it? Well, there are weather analysis that I explained earlier what that was, that are available and that were produced at the global scale by the European and a few other groups. But the time resolution is 6 hours, and the space resolution is a bit rough. So what we can do, though, is start with these. They go far in the past and use our modern weather forecast model and initialize them with these past analysis, and then produce new forecasts in the past. And then this allows to produce a coherent data set of forecasts. And the forecast models will be able to provide a lot more details, like temperature at every 15 minutes, more spatial resolution, higher spatial resolution, and also interesting is to have something very coherent the data. And we're looking into producing this kind of reforecast. So on the next slide, I'm illustrating a project that we're working on. And the project is just starting, and the intent is to produce a coherent data set that will be valid across North America at the 15-kilometer resolution. And once this is available, and this will be valid from 1979 to today, and we'll keep updating that afterwards. And we hopefully with time, we'll be able to even improve on that. For example, in the future, we may reprocess again all this, but at a higher resolution or with better weather models. The air quality part of it is not included yet, but it's the kind of things that we're considering. The challenge with air quality is that in order to do such a reforecast for air quality, we would need emission data sets that would make sense for the past, and this data is becoming very difficult to get. So that covers it. On the last slide, you have also my colleague Sylvain, who is in our contact with the CANUE group. Yes. Yeah, first question was, I think, about multi-pollutant. Yes, it's a multi-pollutant approach, and the chemical reactions for air quality are in balance. So, for example, it includes secondary production of secondary aerosols. So the PMs in the model are not only and represent various species of PM, like nitrates, sulfates, etc. So it's very comprehensive in terms of the chemicals that are interacting. Ultrafine PM data, we have the capacity to produce finer PM in research, but it's not in our operational model right now. So that's the kind of things that could be addressed maybe in the future, but the current capacity, operational capacity does not include that. So ultrafine would be a PM 0.1 or 0.1. Yeah, but that's something we're looking into, but more for the future. Other questions? Reforecast. I see Jeff, you're interested in that, and we'll keep working on it. Be able for future local scale. And okay, the future capacity will evolve in terms of resolution, but for example, for air quality, we'll start running a 2.5 kilometer resolution in around maybe or something around 2020. And at that time, maybe we can look back if we can process data sets in the past, but that's something that's not coming very soon. There's still a bit more work to address higher resolution. It's really a question of computational capacity, mostly. And for climate change scenarios, that's something that's being addressed a little bit in research mode, so we can do scenarios in the future for a future air quality. And we're aware there's demand for it. But it's something that's emerging in terms of capacity. And using ground cover, last question maybe, and climate zone. And for, well, that's something maybe Sylvie can address, because that's something that is more relevant when we get to higher scale, finer scale. So maybe we can turn to Sylvie now.
So I'm continuing with an overview of the urban and high resolution numerical weather prediction. So you can go on the next slide. So this to include the urban processes in the weather models, it has started a few years ago now, and there are several projects, research projects about understanding the physical processes in the urban area and evaluating the models with different data sets, observational data sets. So it started with a project CRTI in Montreal and Oklahoma City, and an EPIC environmental prediction in Canadian cities project. This was a CFCIS project, and there were long-term measurements in Montreal and Vancouver. So it allowed to evaluate the new urban scheme, the town energy balance model that is included in the weather prediction system. Then more recently, there has been the Pan American Games in Toronto, so long-term project with a lot of work on that. Then in parallel, the TOMAX project, it was on Tokyo, and there are experiments focusing on extreme weather events, especially on the high precipitation in the city. And recently, we have started a project with the National Institute of Health in Quebec about looking on Montreal and to look on the effect of mitigation strategies on the heat in the city. So it's a recent project, and so now the system have now mature enough to be included in the operational system. So it's ongoing, and it's probably coming soon. So next slide. So this is an overview, simple overview of a quite complex system, but so just the main focus here is the town energy balance model, the surface scheme that deal with the physical processes in the city, and also it's linked with vegetation scheme. For that, we need a representation of urban canopy, and also so it's linked in a different way. So we have two systems. So the first system is a 2D system that you have. Some of you have have seen as a GEMSURF system, or also now it's called SPS. And the surface skins are driven from atmospheric forcings that can be used in archives, so different types of archives, so it's very flexible. For that, we did also the assimilation, data assimilation at the surface. And more complete tool is the 3D interactions with the atmospheric model. So it costs more. It depends on the application, but for numerical weather prediction, we certainly mostly use 3D. And 2D for longer term predictions, or also other as it was used as you showed for the ICES project. So that's it. Okay, next slide. This is a way to represent how we deal with the physical processes in the urban area. So this is about the scale we consider in the model. So there is no exactly limit of the scale, but basically we use a grid spacing of 100-200 meters. So we consider the different processes like conduction in the buildings, inside and outside the buildings, the turbulence in the streets and above at the roof levels also, and the radiation, solar and infrared. We take into account the reflections in the canopy. So that it allows to see the effects of storage in the buildings and release heat during the evening that are responsible for the urbanite islands, and also the obstacles from the buildings that provide a change in the wind. Okay, so you can switch next slide. So this is an example of first study with the 2D system with the urban processes over Montreal. So the simulation was provided at 120 meters, and so we compared with in situ measurements, but we wanted also to have an overview of the spatial variability of the model. So for that, we used satellite imagery, and we upscaled the numerical output at the same resolution. And we compare for several satellite data to see that we really improved the weather forecast with these processes. Next slide. More recently, so in the context of the Pan Am Games, there were multidisciplinary team, and there was a interest to include heat stress indices in health related platform, experimental platform that was called Wisdom, and so they have used for example the basic parameter, meteorological parameters like temperature, the wind and humidity, but humidex, but also the new, the more advanced heat stress indices, UTCI and WBGT. So it could be implemented in this focus, and this is an example on one day where you can see the influence of mesoscale, like the lake breeze effect that can be seen even on the heat stress indices. Next slide. So we have maps of new maps of those heat stress indices that can be used for health decisions. But we wanted to look at the physical process to make sure we correctly model it, and so we use the Pan Am network with the globe temperature, the black globes that you can see here, and as you can see, this is in clear sky condition, we are able to represent the diurnal variation. Next slide. And so finally, so the Pan Am was more focusing on very high resolution subkilometric at 250 meters 3D. so very time-consuming system. But in parallel, it has been recognized that we need to put those processes in the HRDPS 2.5 kilometer system that hopefully will become the operational system very soon. So this is the representation for the national grid for the urban area fraction. So it's so you see in Canada and over a lot of influence also in the United States. Next slide. And this is just trying to summarize how we did. We obtained the surface characteristics for the HRDPS and also for Toronto. So we have GIS systems to combine different, in general, free available data sets, and for example, we use. It's a mix of vectorial and other data sets, and we provide 5-meter land use land cover with also attributes, and then we can obtain the parameters that we need in the TEB model directly at the grid point. It's different than having a homogeneous zone like local climate zone that people are using. We decided to specify grid points parameters, and then some parameters for the model are grid cell aggregated and represent the canopy in the model at the resolution of the model. So next slide. And so the HRDPS 2.5 kilometer was tested with the TEB model, and this is some results for the USA, and this is we see an improvement of the bias in the temperature from the control experiments. So this is it's not exactly the same result for all the regions, but in general it's very positive. Next slide. Okay, so as I mentioned, it should be included in the official 2.5 kilometer HRDPS very soon, and hopefully operational soon. And then, so this is the operational system first, 2.5, but then there is also is recognized interest to go even at higher resolution at 250 kilometer. But as it's more consuming, it will be certainly focusing on the main Canadian cities first. And this is coming in probably in the next year or next 2 years. There is also objective evaluation of the system during the PANAM. Also, there are the evaluation of mitigation strategies. So by modifying the land surface description, and this is not a big project, but we start to do this kind of thing. And so also in a similar way that Didier presented, we could also use a Reanalysis at 15 kilometer together with the 2D model. Next slide. I think that was finished. So, thank you.